All right, guys, let's get into section number 1. In section number 1, we're going to be talking about designing EIGRP, the Enhanced Interior Gateway Routing Protocol. EIGRP has been around for quite some time. It's been around, since the mid-90s, I guess, and prior to that, IGRP existed, of course, the predecessor to EIGRP, but EIGRP certainly has grown quite a bit from what we typically saw with IGRP. EIGRP is a distance vector routing protocol. Now, what does that mean? That means as a routing protocol, it doesn't have a complete understanding of the entire topology. It does what we call routing by rumor, meaning that it makes decisions based on information that it hears from its neighbors, but the neighbors only share certain information with their upstream peers. In fact, EIGRP routers only share what they use with their upstream peers. They don't share everything they know. So by the time I get to the end of the line, router A is making a decision based on what router B decided, based on what router C decided, based on what router D decided. We call this routing by rumor. And that's a traditional distance vector concept. Now, there are some benefits to this approach. One of the benefits is a more relaxed topology design. EIGRP sits in what we call a flat architecture. OSPF uses a spine and leaf architecture where we have multi-area designs. You have a backbone area and you have your non-backbone areas, whereas EIGRP sits in a single flat autonomous system. And now the benefit to this relaxed topology is that we have the ability to do things like stub routing features anywhere in the network, as well as summarization anywhere in the network, as opposed to OSPF, where we can only summarize on an area border router or an autonomous system boundary router, and we have to have a very, very specific design. There is a downside to this design, of course. The downside to this relaxed architecture is that it's not as scalable. That's a relative concept, right? EIGRP can scale to hundreds of routers in diameter, and that will fit in most organizations. But OSPF certainly can scale to a much, much larger environment in a multi-area, a well-designed multi-area design. All right. But the nice thing about having this kind of more relaxed topology is the ability to summarize on any node in the network. And we will talk about summarization a little bit later on and how summarization is going to influence our decisions on how we do routing and so on. We can also configure stub routing features pretty much anywhere in the network as well, although certainly there are routers that we probably wouldn't want to configure as stub routers. And then there are some routers that we would want to configure as stub routers, but we'll talk about that concept a little bit later on. All right. As far as convergence goes, there's always two things that you consider when you talk about a routing protocol. Number one is how quickly does the protocol handle changes to the topology? Additions of networks, changes in metrics, overall just changes in the topology altogether. EIGRP actually, if it's designed correctly, converges faster than just about any other routing protocol, meaning that you have a successor, you have a feasible successor, you're doing your stub query scoping. We'll talk about that concept a little bit later on. You're implementing your summarization at appropriate summarization boundaries with your contiguous address blocks and whatnot. EIGRP can actually be designed to operate very, very efficiently. All right. So convergence is something that we always try to consider when we're choosing a routing protocol and when we're choosing to implement a routing protocol in a particular topology. The other thing that we consider is scalability. And scalability can come in different factors as well. Some might argue that EIGRP is in fact more scalable because it has this kind of arbitrary design where you don't really have all these design restrictions on where areas have to be placed and how routers have to be connected to the backbone and the backbone has to be contiguous and so on. EIGRP doesn't have any of those limitations, but There are some things that EIGRP lacks in scalability, certainly how it deals with topology change notifications and be able to propagate those changes. That routing by rumor concept, as opposed to having a complete picture of the topology, is something to consider as well. Now, we are going to talk about summarization. We are going to talk about query scoping, but we're going to talk about some of the other elements as well to offer fast convergence. Things like bidirectional forwarding detection, or BFD, which is not really specific to EIGRP. It's a protocol that we can use with any routing protocol. This is to have sub-second neighbor loss detection, even with neighbors that aren't physically connected to each other. Logically, they're connected to each other, but there might be a switch in between or a cloud in between, and neighbor loss detection would have to rely on, traditionally, dead timers or hold timer expiration in order for us to be able to identify that a neighbor doesn't exist. With BFD, we can reduce that, that notification and that identification relatively quickly. Graceful Restart we'll talk about, and what we call Cisco non-stop forwarding. We'll talk about that concept as well. So there are many elements that we can add to EIGRP to actually make it more scalable and faster to converge. Again, as I mentioned, EIGRP is a relatively easy protocol to work with because we don't have all of the restrictions that we would have with, say, OSPF, with regard to where we can do summarization, where we can do things like filtering, the flexibility that we have with different network types. OSPF is kind of very particular about the different network types it has. But the protocol itself has a lot of functionality that OSPF doesn't. That arbitrary design is really the key element here. When we say arbitrary, it means basically that we don't have to follow a strict design code like we do with OSPF. In OSPF, if you have a multi-area design, there are a bunch of different checkboxes that you have to check in order for that design to be sustainable. A contiguous backbone area, only 50 routers in an area, give or take. It's not a hard, fast number, but give or take 50 routers in an area. Non-backbone areas have to be directly connected to the backbone. We can only summarize on an ABR or an ASBR and so on. OSPF has those restrictions. EIGRP doesn't really have those restrictions. So even though OSPF uses this structured hierarchical approach, that hierarchy does provide for a lot more scalability and a lot more functionality. It does limit us as well. Now, scalability in EIGRP is going to depend on two primary elements: summarization, right? Where are we going to do summarization? In EIGRP, we summarize on the interface. We don't summarize from an area or into an area. Excuse me. In OSPF, we summarize out of areas. We summarize on the interface, and we can summarize in that direction. We can choose to summarize in that direction. And that's the nice thing about EIGRP, is that we have that ability to do summarization and even filtering of routing arbitrarily in the topology. We in OSPF, as an example, every router in the OSPF area has to have the same topology database or link state database. So even if I am applying filtering, I can limit what goes into the global RIB, into the global routing table, but I can't limit what goes into the link state database, because if the routers don't have a common database, it is going to cause some major issues with EIGRP convergence, OSPF convergence and so on. All right. Now, with EIGRP, we still have to consider things like contiguous address blocks, being able to have these contiguous address spaces. We can't summarize or we risk the possibility of having possibly overlapping summaries and so on. But as long as you're following some of the basic rules in design, right? One of those rules, for example, being that longest match routing always takes precedence. You can kind of get a little creative with how you're creating your summaries and how you're advertising your summaries and so on. All right, so summarization, I mentioned it probably 100 times already in the 10 minutes that we've been speaking, but summarization is a key element to actually scaling any routing protocol. It just so happens in EIGRP that we can summarize anywhere in the network. All right. Now in OSPF, like I said, we have a very, very structured design that we have to follow. And that structured design is pretty critical, right? Area 0, and we have some scalability things that we have to consider as well. Now, the other component of EIGRP that provides us the ability for scalability and fast convergence and whatnot is how do we handle not only our primary routes, but how do we handle our backup routes, right? OSPF doesn't have this feature built into it natively. There is a concept in OSPF where you can configure essentially the equivalent of a feasible successor. It's called a OSPF loop-free alternate route. But in EIGRP, the concept is built in to the algorithm. We use dual in EIGRP, the diffuse update algorithm or diffusing update algorithm. And that algorithm is pretty critical to how EIGRP functions. And part of that is to select not only our best route, which is our successor route, but also to select our next best route, which is our feasible successor, as long as that feasible successor meets the feasibility condition. All right. In essence, what OSPF. In essence, what EIGRP is doing when it calculates a feasible successor is it's choosing essentially the next best route. All right, so if the primary route fails, we can immediately start routing packets using that next best route, assuming that we've been able to verify that it is a loop-free alternate path. And what I mean by loop-free alternate path is that it isn't included in the original path. That's a very, very important concept. And we do that by checking something called the feasibility condition. The reported distance of the backup path has to be less than the overall feasible distance of the primary path in order for us to consider that path a feasible successor. I'm not drawing this in a diagram. I'm not even referencing a diagram in this case because this class is not intended to teach you those theoretical concepts. It is kind of assumed that you understand those basic concepts when you come into this class. Of course, Encore and ENARSI, the Advanced Routing and Services class, would prepare you for that. The idea here is how do I apply those theoretical concepts to a good design? And that's what the Enterprise Design course is all about. So you'll hear me talk about a lot of these concepts. You'll kind of see not a whole lot's happening on the screen. We're not seeing a lot of changes. That's because really these are concepts that are covered in other courses. All right. Like for example, what happens when I lose my successor and I don't have a feasible successor, but maybe I have another path that's available. So I have an alternate path. It didn't happen to meet the feasibility condition, but it is still another path. Well, we have to go to a secondary process to determine whether or not that path is part of the original path or not. That secondary process is the concept where we go into deciding is this path part of the original path by sending out something called a query. An EIGRP query allows me to identify whether or not the path is still valid. Those queries can be flooded throughout the entire autonomous system. And of course, we have to wait for responses. I say, of course, as if you guys know that, but we have to wait for a response from our downstream hosts that we queried before we can actually send a response to our upstream hosts that queried us. So it's a really, really big concern in EIGRP to make sure that we understand how the query process works, what devices would I query versus what devices would I not query, We'll talk a little bit about that in this class because that is kind of a design element. But again, it's really a feature or a concept that you should have already learned in some of your other courses, right? Summarization is a big key. Where do we do summarization? Stub routing is a big key. That's how we limit the queries in our overall design. Implementing prefix lists and route filters and distribute lists and so on. Also another important concept. And that's one thing I hadn't mentioned yet. The third and final piece to this is how can I limit the amount of information that I share? Because I may not have to share everything. All right. And by default, IGP neighbors, interior gateway routing protocol neighbors, automatically share everything with their peers once they become a peer. So we would have to do some sort of filtering to kind of limit that. All right. So it is a consideration that we have to take into account. Now, EIGRP does provide the ability for us to create this hierarchical design. All right. Now, when we take a look at, even though EIGRP doesn't have the concept of an area, right, we can still design into the protocol kind of a way of limiting the amount of information that has to be shared, right? By creating this architecture or this tiered architecture that allows us to create nice, clean summarization boundaries, nice, clean areas where we can actually maybe potentially say, okay, we're going to limit the queries that go down to these routers and so on. But what you're seeing in this particular diagram here is a basic concept of zones that we're applying to the topology. And those zones actually, you can see the blue circles here represent what we call choke points, right? Here, here, and here. And those concepts, the concept of creating these zones is, kind of an idea of what we might consider in OSPF is like an area, basically logical parts of a network where devices are commonly communicating to each other. Or they belong to maybe a hierarchy of address space within that area and so on. But the choke points themselves are where we interconnect the zones together. And those choke points is where we can implement policy. And that's a really, really important concept, especially with the EIGRP. Because it is an arbitrary design, we have the ability to kind of implement policy at really kind of any point in the network. All right, so these zones are basically just kind of logically defined parts of the network. They represent what we call a failure domain. If a device in that area fails or a link in that area fails, it should not have a vast effect on the other zones that we have created. All right. This is a very, very, what term am I looking for? Kind of I wouldn't say a theoretical concept. That's not the term I'm looking for. It's kind of a in the cloud kind of concept, right? There's no hard, fast design rule that says you should create zones based on A, B, and C. It really just depends on how your devices are interconnected, how many devices you have, and so on. All right? But those choke points represent basically the places that you would apply things like filtering, like summarization, possibly stub routing features where you might limit the scope of the queries by implementing some sort of stub EIGRP routing feature. But the biggest key probably is the summarization piece. That's where we can also aggregate traffic flows and define traffic policies, manipulate routes, apply different metrics to different paths and so on. All right. Now the question in OSPF pretty typically is, okay, what is going to comprise my backbone? right? And that's generally based on some sort of physical design, physical architecture design. Devices that go in the backbone allow us to interconnect all of our non-backbone areas. And then, of course, what would be my non-backbone areas, and how would I allow for redundancy and connectivity from one non-backbone area to the other. In OSPF, it's relatively simple because we have a spine and leaf design, and there's quite a consensus on how a redundant spine and leaf design should look. In EIGRP, it's a little bit more, gosh, I can't think of that dang word that I'm trying to think of, but it's a little bit kind of more out there, right? I think you guys understand what I'm trying to say. There's no hard, fast rule, right? How many layers should I build into my design? You can build in really as many layers as you want, because again, we're not following any kind of strict architecture rule. It's still arbitrary, but keep in mind, typically the design is going to have a couple of different layers, and between those layers we have our choke points, and the choke points is where we're going to implement summarization and so on. All right. If you have, Cisco recommends, of course, if you have only a small network, maybe you have a couple of layers, one that might consist of really kind of a virtual backbone, if you will, and the other might consist of your non-backbone. But the topology depth is something to take into account. You have more layers, you have more topology depth, more complex design, and so on. All right. Now, how do we achieve fast convergence with EIGRP? We've kind of already talked about this a little bit, right? Convergence in EIGRP, one of the key elements to fast convergence is to implement route summarization. Now you might say, well, wait a minute. Route summarization hides network layer reachability information, essentially. I mean, that's ultimately kind of the goal of route summarization, is to reduce the size of your topology database or your routing specific rib, like EIGRP rib, and then reduce subsequently the size of your global rib, your global routing information base. But summarization can also help with convergence in a sense that if the summary is valid, then routing doesn't have to be recalculated. If I have a router here, for example, and I'm summarizing, 1,000 different networks out to a peer, right? As long as one of those networks exists in that list, the summary will be advertised. So that summary route is still going to be advertised. Maybe it'll have a different metric. The metric depends on essentially the routes that are included in the summary. We always take the lowest metric for whatever routes are included. But the point is, if this network goes away, that summary doesn't change, which means that router doesn't have to run dual. That router doesn't have to reconverge. It doesn't have to send a query, those kinds of things. Now, the flip side to that is that router still thinks that that network that went away is available. So it's still going to be routing packets to that destination. And then ultimately the null zero route on this router will end up dropping those packets because the more specific route no longer exists in the local routing table. All right. But what's worse? Is it worse to maybe send a few packets to a destination that ultimately doesn't exist and the packets are going to get dropped? Or is it more detrimental to have to recalculate my entire database, rerun the dual algorithm, and recalculate what routes go into the routing table? Some might argue one is better than the other. I guess it really depends on how many routes you have, how large the databases are, how much memory the routers have, their ability to recalculate that information quickly, the ability for that information to be propagated quickly, as opposed to packets being routed. You'll find this with this class quite a bit. There isn't really any specific golden rule, right? It really does depend on kind of what you're doing in your network. Now, the point to take away from this is you have to understand what the options are. You have to understand what the impact is of doing something as opposed to not doing it. or vice versa. Not doing it as opposed to doing it. What are the potential drawbacks? What are the potential benefits? That's what design is all about. Equal cost paths, certainly equal cost paths can help with convergence because certainly if one of those paths goes away, we can still route using the other path. But again, EIGRP is actually the only routing protocol that really can do it. Unequal cost path load balancing is an option as well. Now, I wouldn't say that this is necessarily directly related to convergence, because convergence to me is a concept in which something fails and you have to calculate an alternate path, whereas equal cost path, we've already got another path. We've got multiple paths actually, and if one of them fails, then basically the other path will simply take over, all right? Or continue to work as it was because it was part of the routing information anyway. This is really critical right here. Having a feasible successor, right? So basic concept. I don't typically do this in this class, but I will go ahead and do a quick crash course in feasible successor calculations. So let's say that we have these two paths to reach network X. And let's say that the top path has been chosen as my successor path, okay? So that top path has been chosen as my successor path. Now, EIGRP takes it one step further. OSPF would stop at this point and say, you know what? I have my best path. I don't really need to do anything else. I'm just going to kind of sit back and, do my routing. But EIGRP, being a distance vector routing protocol, not having a complete picture of the topology, has to figure out a way of converging faster, because if we didn't have this concept of feasible successor, we would have to literally re-exchange and recalculate routing information on every single router. So what EIGRP does is it says, you know what, we've got our successor path. Let's go ahead and choose a loop-free alternate path that we classify as our feasible successor. That feasible successor is chosen based on something called, the feasibility condition. And the feasibility condition states this: yes, it is going to be a feasible successor if the reported distance of that potential feasible successor path is less than the feasible distance of my current successor path. Now, there's a reason why this formula works, because if the reported distance, which is the distance for the neighbor to reach the destination, is less than the feasible distance of the successor path, then that path, that alternate path, can't be part of the original path. In other words, let me change my pen color here. In other words, if the bottom path, what happened to my mouse? Where did my mouse go? My mouse has disappeared. Let's see. Oh, there it went. I just saw it fly by. All right. So in other words, if this distance, this metric, which is the reported distance to that neighbor, if that value is less than the overall path metric for that path, then there's no way that that bottom path can be inclusive of the top path, because if it was inclusive of the top path, it would be higher. So that feasibility condition check is really, really critical. And that's what allows us to choose that backup route. All right. So let's say it meets the condition. Let's say that the metric for the top path is, I don't know, we'll call it 1,000. And the reported distance for here is 500. Now, some people might say, well, wait a minute. If the reported distance is 500 and the top path is 1,000, why didn't I just use the bottom path as my primary path? Well, you have to consider there's still the cost of this link as well that gets added to the reported distance. It's called reported distance because it's the distance that the neighbor reports to its peer, which is the neighbor's successor. Well, I wouldn't say that. The neighbor's feasible distance to the destination. Okay? So you can see why this is an important concept to understand. Now, you might not always meet this requirement, right? In this case, we do meet this requirement. So this path is a feasible successor. If the top path fails, we immediately start routing over the bottom path without having to do any kind of calculation. All right. When I teach my introductory routing courses or even get into my advanced routing courses, I always tell my students that it's important that you understand this feasibility condition. Even though it's automatically calculated and you don't really have to do anything, if you don't have feasible successors, and it simply may be that you don't have a feasible successor because the metrics don't add up. That may be the only reason. It may mean, there may be a valid alternate path that does not include the original path, right? But just because the metrics don't add up, it just simply didn't qualify as a feasible successor. So what would you do as an engineer to fix that problem? You would manipulate the metrics manually so that EIGRP thinks it has a feasible successor. All right? And so that would then in turn stop the query process, which means convergence would happen faster and so on. So just because an alternate path is loop-free doesn't mean it automatically meets the feasibility condition. It has to meet, or it doesn't mean it automatically becomes a feasible successor, I should say. It has to meet the feasibility condition. Sometimes you have to force that to happen in order for it to happen. It's just the way the math works. All right. We'll talk more about this other concept as well, configuring leaf nodes as stub routers. I'll give you a little quick crash course in this, right? So you have maybe a hub and spoke design where you've got various branch locations that are connected to your network. This is your headquarter location, and behind the headquarters, you have your thousands of routes that exist in the headquarters. And then behind these locations, you got, a couple routes there, a couple routes there, a couple routes there. Well, if one of those 1,000 routes goes down, by default, the first thing that the HQ router is going to do is it's going to send out a query to the spoke routers for the network that it lost, because there is no feasible successor. Whenever there's no feasible successor, I send a query. But there's no reason for HQ to query the branch routers for prefixes that the HQ router originates, or at least, that these branch routers have to go through HQ to get to those prefixes. So this is a design scenario where you'd say, let's go ahead and set up those branch routers as stub routers, because stub routers don't get queried. There's other features of the stub routing concept. We can limit what we share with upstream routers as well. But this is what we refer to in the design elements of EIGRP as EIGRP query scoping, where we're limiting the need to send out queries because those queries have to be sent, they have to be repropagated down the line, and they have to be replied to in order for us to converge. All right? If there's no reason to query a router because it's a stub router, meaning there's only one way in and one way out, then go ahead and set up that router as a stub router. Now, we do have different stub features that are available: stub summary, stub connected, stub static, stub redistributed, stub receive only. And all of those do different things. It has more to do with what the router shares with its upstream neighbors as opposed to whether or not the router gets queried or not, but that's a whole nother discussion. All right. Now it does say there, avoid non-stub routing peers. Now, what do they mean by avoid non-stub routing peers? Well, if you take it literally, it's kind of contradictory to what we just talked about, right? Which is to set up routers as stubs. But when they say avoid non-stub routing peers, they mean that we have redundant paths. So we can get successors, and we can get feasible successors, and we can have load balancing and load sharing, unequal cost, equal cost, whatever it might be. We do that by having non-stub routing peers, meaning that we share everything with those peers because we have a reason to. There are alternate paths that we can use. Stub routing peers kind of don't really lift their own weight. All right, they don't pay their own way, so to speak. They're really reliant on other devices to communicate, and they only share a limited amount of information. All right. So the bottom line here is you have to design the network properly. Summarization is going to limit the scope of queries. Summarization shrinks the number of entries that you have in your routing table. That's also going to speed up CPU operations on the router itself. In the past, that might have been a bigger concern, right? When routers had kind of really bad CPUs or slow CPUs. Now we don't really concern ourselves with that as much. We concern more, with the need to run the algorithm, the dual algorithm, and that's where the absence of a feasible successor comes into play. Make sure you have a feasible successor in the routing table, or I should say the topology table. Feasible successors don't go into the routing table, but you could have also ECMP, equal cost multipath routing, or UCMP, unequal cost multipath routing. And we would tune metrics to do that, right? Tune metrics, bandwidth, delay, etc. You have to be consistent with that, right? When you're modifying metrics, you have to understand the impact of that metric on not only the overall path metric. It's a really, really important concept, but also how is that going to affect successor, feasible successor? Okay. Now, as far as actually scaling EIGRP, it really depends on how much of these features you implement. If you're doing route filtering, if you're doing summarization, if you're doing query scoping with stub routing features and so on, you can achieve really, really fast convergence in a relatively large network. We always talk about scalability of a network from two perspectives: density and diameter. Density is a term that we use to describe the number of paths. Just because you can get from point A to point B doesn't mean that's a relatively simple network. Because you could have a simple network that to get from point A to point B, there's only one path. Or you could have a scenario to get from point A to point B, there could be 100 paths. That's the density of the network. All right. So the number of peers that I have, the number of alternate paths. For example, if you go out to the looking glass, the BGP looking glass, and go into a BGP route server and take a look at one of the routing tables, you'll see that they identify how many destination prefixes exist, but they also identify how many paths exist. That's a really, really important concept in scalability. It's not just about how many destinations you get to, it's about how you get there. All right. So it really depends on how you implement those features. But hopefully with this initial kind of introductory section here, you have a pretty good understanding of the tools that you consider when you're thinking about designing an EIGRP network, right? We're basically talking about three things outside of the basic configuration, right? Achieving convergence, achieving adjacencies, that kind of thing. But scalability is not about the initial achievement of convergence and adjacencies. It's about how we handle changes. And that is the three things that we mentioned: summarization, query scoping, and route filtering. We haven't got into the details of filtering just yet, but we will. All right. Now, EIGRP being an arbitrary design, it uses something called an autonomous system to achieve the implementation, if you will. Right? An EIGRP autonomous system is a collection of EIGRP routers that share a common database, if you will. It's not quite the same as OSPF. It's not actually identical, but basically they're essentially identifying the same network layer reachability information. All right. If you have multiple EIGRP autonomous systems, there are some considerations to take into account. Now, in this particular topology, we're seeing a couple of things happen here. We've got a redistribution point here. That means we're taking routes from RIP and we're sending them into EIGRP. Now, there is a concept in routing called administrative distance. Administrative distance is a big thing to consider, especially with EIGRP. The default administrative distance for internal EIGRP routes is 90, and the administrative distance of external EIGRP routes by default is 170. So you have to consider what the effect is of redistribution or redistribution if that's happening. Now, that's not necessarily the scenario that they're describing in this particular case, but we definitely have redistribution taking place, which is always, in my opinion, the first thing you think about is, okay, how is redistribution being done? And is it introducing some sort of suboptimal routing scenario where, we're not routing the best way possible? All right, so we're redistributing a route from RIP into AS200 in this particular case. A then redistributes routes into AS100. Now, that's not as problematic because it's EIGRP to EIGRP. All right, but let's continue to walk through the scenario here. Router B is going to receive that route from AS100 and AS200 because it happens to be participating in both of those autonomous systems. Because the same route is learned through separate routing processes, the route that gets installed first is the one that ends up being preferred. We can't do a tiebreaker based on administrative distance because it has the same administrative distance in either case. When I redistribute from AS200 into AS100 on router A, it was already 170 when it came into here because it was redistributed into AS200 through RIP, and it stays 170 when it gets over to here. So we can't use administrative distance. And the same thing here, it would have shown up on router B as an AD of 170. Okay? So we can't use administrative distance as a tiebreaker. We can't use prefix length as a tiebreaker because it's the same prefix. And we can't use the metric, right? Yeah, maybe we could. I guess it depends on how you seed the metric when you redistribute from one protocol to the other. They don't really give us enough information here to really decide that, but it's actually likely, frankly, that the metric would come into play because the metric would be seeded on router C from RIP because we can't do hop count into the complex metric that EIGRP uses. But if we're redistributing from one EIGRP AS to another, the metric information is maintained because the EIGRP process understands bandwidth, delay, reliability, and load, and K values and everything else. So long story short, I think this is less of a problem than they probably presented, but it's kind of a generic scenario, I think, in this case. I don't think they're intending this to be a real kind of super scenario that you have to consider. All right. I guess they describe it as a potential issue. A route is being redistributed from RIP into AS200. Router A redistributes that into AS100. Router B hears about that route prefix in advertisements from AS200 and 100. The AD is the same because they're both external. They already became a 170 from RIP. Based on what they're saying, the route that gets installed into the topology database is whatever's placed into the routing table first. I'm not actually entirely convinced that that would be the case. Now, maybe if AS100 wasn't EIGRP, maybe it was BGP or some other routing protocol, definitely something to consider there, especially when it comes with administrative distance. If that was OSPF, a redistributed route into OSPF has an AD of 110, B would prefer the path through A to get to RIP, even though C might be better. All right. So maybe not a really good example in this particular case because other things to consider, particularly how the metric is handled. But let's continue down this path, right? Let's talk about the query process. Now, I already mentioned this before. A query is sent when I lose my successor and I don't have a feasible successor. So let's say router C sends an EIGRP query to router A. Router A sends that query to its neighbors. That's how queries work. You query me, I query my neighbors, they in turn query their neighbors query their neighbors, and so on. All right. Now, before I can respond to a query, I need to get responses for the queries that I've sent. That's just the rule. In the past, we had a process in how we dealt with queries that remained out there for too long. It's called a stuck inactive query process. After 3 minutes, if I haven't received a reply from you, then I am going to go ahead and assume that you don't exist anymore. I'm going to delete the neighbor relationship that I have with you. Now, we could run into a scenario where router A queries router B, and router B queries router C, and so on, and router C queries D. And maybe there's an issue here, right? There's something going on that link that is preventing router D from responding to router C. All right, now this query has already been sent out, and that query has been sent out, and that query has been sent out. But because D cannot respond to C, in turn, C cannot respond to Bravo, and Bravo cannot respond to Alpha. And what would happen is after 3 minutes, I would go into stuck inactive, and I would delete the adjacency that I had with that peer and reestablish the adjacency with the peer, assuming that most likely I'm not going to be able to because I couldn't get a query reply. So there must be some other things happening, but there really was never a problem between those two routers. The problem was downstream. All right, but it's a chain reaction because if D doesn't respond to C, C can't respond to B, and B can't respond to A. And because A queried B first, most likely that 3-minute timer is going to expire between those two peers prior to any of the downstream router timers expiring between the other peers. So they added a new feature. I think it was in 12.0. Don't quote me on that, but I'm pretty sure it was around 12.0 or 12.1, called a stuck inactive query. All right. So after 90 seconds, we will send a stuck inactive query, but that stuck inactive query is between the neighbors directly. So that router can respond with, I got your stuck inactive query, man. I'm not the problem. Okay, now you know I'm not the problem. Somebody downstream is causing an issue, and I'm just sitting here waiting for that downstream router to respond. You can see, though, where this could cause some issues, particularly if you have a lot of neighbors and you have a lot of routers that have to be queried. So the idea is that we want to limit how these queries propagate. All right. Now, continuing on with the scenario that we see in the diagram here. Again, router C sends an EIGRP query to router A. Router A sends the query to all of its neighbors, including neighbors in AS100. We don't discriminate. Doesn't matter where what autonomous system the query came from. If I have downstream neighbors, I have to send that query on, because a query is essentially somebody looking for how to reach a destination. And that destination may or may not be within my own autonomous system. All right. Router A replies for AS200. It sends the query into AS100. But if router B, if the timing is right or whatever, router B would have already received and replied to the query from router C as well, because they don't have it drawn here, but we have to assume that router C probably has, based on the previous diagram, some sort of neighbor relationship or adjacency with router B. All right. All right. Now, the query wasn't stopped in this case. It was delayed, but it wasn't stopped. Now, in this particular case, the point of this whole discussion is that even if you design a multi-tiered architecture, in other words, you've kind of tried to create this multi-tiered environment with the EIGRP, utilizing multiple autonomous systems, it has no effect on how queries are processed. None whatsoever. Queries propagate through autonomous systems. So using multiple EIGRP autonomous systems doesn't result in any positive gain, right? We use summarization, we use distribution lists, we use stub routing features, but we do not use multiple autonomous systems. Okay. There are some kind of key points that they document here in the book, right? There are several reasons to use multiple autonomous systems, but be careful. But careful attention must be paid to limiting the queries. Multiple autonomous systems are never considered to be a permanent solution. Typically, it's a migratory solution where maybe you've acquired another organization or another company, and you're in the process of trying to merge the domains together so you have multiple autonomous systems. It's much more complicated. Redistribution does happen automatically, and the metrics are copaesthetic, right? The EIGRP understands what the metrics are, but you still have some things to consider. All right. So one of the kind of general ideas is that you create a similar type of spine and leaf topology with the EIGRP that you would see with OSPF. It's just a little bit more theoretical, I guess, as opposed to actually definable like we have with OSPF. But just like any tiered architecture, the spine, which really is kind of the two top routers in this topology, is only designed to do one thing: get packets from point A to point B as quickly as possible. There should probably be some sort of connection here or something. But get packets from point A to point B as quickly as possible, right? That's the whole point of any core in any network. Even if you're talking about a 3-layer architecture, right? Like where you have the access, distribution, and core. The core layer is only there for transport. That's its sole purpose. All right. So don't do any policy inside the core. Don't implement security. Don't do things like aggregation. We should summarize routing information towards the aggregation layer as best as possible based on the hierarchy that we have in our addressing scheme, mainly that we have contiguous address blocks and so on. But don't implement routing policies necessarily in the core. Implement routing policies, towards the kind of the second layer, if you will. The aggregation layer is what they're referencing it here in this particular case. That's where you have all your attachment points for your devices. All right. Information about those edge devices should really be hidden from the core. And again, we do that through basic route summarization. I might have 20 or 30 or 40 subnets down at the aggregation layer, but as long as they're contiguous address blocks, only advertise those subnets as a single subnet going up to the core. All right. Now, this is very different than what we see with OSPF, because in OSPF, the way that we did this is we did it using areas, and we used specific types of routers, area border routers, to be able to facilitate this. Not an EIGRP. EIGRP has a arbitrary network design, and as such is limited in really defining that overall summarization boundary. In OSPF, we can only summarize on an area border router, right? In the EIGRP, we can summarize on any interface in the topology. Okay? All right. Okay, so we have this 2-layer architecture, but we also have a 3-layer architecture that is available to us as well. 3-layer architecture is very similar to what we would see with like a traditional core distribution access type of design. In the 3-layer architecture, the core is still going to be responsible for doing the high-speed routing. And there are some summarization that we're going to do down to the aggregation layer. The points, the choke points between the aggregation layer and the distribution layer is where we're going to have things like policy enforcement, routing enforcement, and so on. The core layer, just like we saw with the 2-layer model, is really just to move traffic, right, across the network, switching packets as quickly as possible. No complex policies, no complex routing decisions. Avoid aggregation in the core itself, directly to other devices within the core. But the choke points that go down between the core and the distribution layer, that's where you're going to be, and certainly down from the distribution to the access layers is where you're going to be doing summarization. Again, kind of a theoretical concept in this case, because we don't really have a traditional core distribution and access design. It's just what they're referencing in this case is our ability to do things like summarization on certain interfaces or certain links pointing to specific destinations in the network and so on. All right. And then, of course, at the access layer, these are going to be the ports that go down to the users. This is where you're going to do your security policy enforcement, where you get to filter off traffic using traditional stateless packet filters like access control lists and so on. And also where you might implement things like passive interface and other features that would allow us to limit the scope of EIGRP down to these layers, all right, or down to these interfaces, I should say. Okay, now there are also different types of logical topologies that we can create. A traditional typical WAN type of topology would be a hub and spoke topology. This is a prime situation in which I would want to configure like spoke routers as stub routers and so on. So we have a default route that allows us to route down to the spokes, but we have our summary routes that allow us to route up through the HQ networks and so on. Again, this is a scenario in which we would want to, we would have multiple spoke routers that are connected to the hub, and the only way that those spoke routers communicate to each other physically and logically is through the hub. That's a traditional hub and spoke design. Now, when we talk about things like DMVPN, Dynamic Multipoint VPN, Phase 3, for example, or Phase 2 for that matter, we have spoke-to-spoke communication that's possible, logically speaking, not physically, but logically speaking, spoke-to-spoke communication. That's not what we're really talking about in this particular case. In this case, we are talking about literally a hub and spoke physical architecture. The hub only is going to advertise a default route from the hub to the spokes. The spokes don't really need anything else, right? The only way that they get anywhere is by going through the hub. So a default route pointing to the hub will be perfect for that. The spoke routers would summarize the spoke networks towards the core, assuming that we have contiguous address blocks. So a 10.1.0.0/22 might get advertised up to, up to the HQ location based on all of the individual 10.1 subnets that might exist on the spoke routers. We can use a /31 prefix on the links between the hub and the spoke to conserve address space. I don't know. That is a concept that we've certainly seen in the past. It's a concept that we see a lot. But the idea of doing a /31 to conserve address space is really kind of an antiquated concept, especially if you're using private addressing in your network and you're not really concerned about whether or not you have an additional address that's being used, and a /30 might be just as efficient. Certainly you can do that on point-to-point links. You can use a /31 because you really don't need a broadcast address. But, are you really going to save that much? This only works on point-to-point links. Basically, a /31 prefix is we apply a 31-bit mask to the interface. That allows the all zeros and all ones IP addresses to be assigned as host addresses on that point-to-point link. Before RFC 3021, I think it was 3021. Before RFC 3021, you didn't have that ability. You had to use a traditional restriction, right? You had a network ID, you had a broadcast ID, and you had two usable addresses within a block of 4 that you would use. Again, like I said, typically when we're dealing with a scenario where we have private addressing, I would say that it's not a big concern, right? Using /30s as opposed to /31s, or even /24s for that matter, private addressing gives us the ability to kind of really be creative with our addressing schemes because we're not really concerned about wasting address space in that particular case. It's very similar to the concept that we see in IPv6, where we have the potential, or the ability, I should say, to really summarize to really large networks, /64s, or at least create large networks, because we just have so much address space that we're not really concerned about conserving address space. All right. Another concept to consider is, what is the scaling capability based on this hub and spoke design? And it actually is pretty significant. Now, if you have no stub routing features, you're going to limit the scalability quite a bit. All right. Now, that would mean that we're not configuring those spoke routers as stubs, but we really should be, right? There's no reason that the hub router should be querying those spoke routers for a route that's disappearing in the corporate network. All right. And the primary limiting factor that we have with the scalability of peers is the this idea that we have, 200 or 300 or 400 spoke routers that we might have to query if the hub router loses a route. If we limit if we limit that query capability, or at least the scope of the query, that's what I was trying to say. That's a new word I created, squery. That's the scope of the query, by the way, the squery. If we limit the scope of the queries by configuring special router types like stub routers, then we can scale up to 4,000 peers on an interface as opposed to only a couple of 100, maybe 300 or 400 peers. All right. The hub and spoke scalability the scalability of that design does really rely on our ability to create those stub routers. Minimize the advertisements of queries to the spokes. Obviously that's going to be based on the fact that we actually have a true hub and spoke design. There's no spoke to spoke communication, logically speaking, and there's no redundant paths in the picture. But we can scale to a much larger environment. All right. If we have over 800 EIGRP neighbors, then that would be probably a good scenario where you would start to consider doing that query scoping. If you have over 1,400 EIGRP neighbors, and that's been done by Cisco in a lab environment, realistically, is that something that you're going to see in your own enterprise? Probably not. You're not going to see networks that scale to that type of size. But again, it's all about applying those concepts, those three concepts that we discussed kind of briefly and maybe in a little bit more detail on some of the concepts, but summarization, query scoping, and route filtering. And we'll get into the route filtering concepts a little bit later on in another section. All right, being that we use distribution lists, or distribute lists, I should say, not distribution lists, but distribute lists, prefix filtering, route filtering, and so on. All right. Now, one of the things that stub features provide us the ability to do is to do something called stub leaking. Remember, stub routing is a two-faceted implementation, right? The first thing that happens when you configure a router as a stub, let's say router C becomes a stub and router D becomes a stub in this particular scenario, okay? In that particular case, maybe this is my headquarters location and I've got router A and router B providing redundancy. We do have a connection between router C and router D. So you might say, well, wait a minute, I don't really want to configure router C and D as a stub because I should be able to, if the link between B and D goes down, I should be able to route through C to get to A, and I should conversely be able to route to D to get to network B and networks that exist beyond router B, right? But configuring stub routing is a two-faceted concept. Not only are we saying, okay, as a stub router, you're not going to be querying me, because stub routers, when they advertise that stub flag in their hello packet, they're basically saying, look, I'm a stub router. Don't query me for anything. But on the second piece to that, we limit what we actually advertise back to our neighbors. So you can see here, connected and summary are the only routes that are being advertised back to router A and from C and back to router B from D. That happens to be, by the way, the default if you just say EIGRP stub. Connected and summary routes get advertised. But notice we have the similar concept between D and C. Now, this is also very important to understand. When you configure a router as a stub, It is a stub for all of its peers. You can't specify which peer you're going to act as a stub for and which peers you don't want to be a stub for. The router is configured as a stub. This is not something that is done on a per interface basis. The entire router is configured as a stub, as opposed to an adjacency being a stub relationships, or an adjacency having some sort of stub relationship. Okay? What happens when, in this particular scenario, when the link between router B and D fails? If I'm only advertising connected in summary, router C receives the 10.1.1.0 route from router D, but it doesn't advertise it to router A because stub routers don't advertise learned routes, at least not by default. All right, they're not going to advertise learned routes by default. So we kind of lose reachability here when that reachability really kind of technically exists. Network 10.1.1.0 is now not reachable from the hub, even though one of the redundant connections between the hub and the spoke is alive in this particular scenario. This will happen in the opposite direction as well. Router C is a stub, so it doesn't end up advertising the default route to router D that it might be receiving. And then as a result of that, router D has no connectivity with the hub. All right. We can actually configure the stub routing feature to do something called leaking. All right. Stub leaking is where we set up basically a way of advertising the prefixes that we want to be leaked, whether we're using a prefix list or an access list or whatever it might be. And we actually go in and say, okay, let's go ahead and leak out the single route that we're learning. Not all the routes that we're learning, but maybe a route that we want to have redundancy for. All right. With stub leaking, we can still limit the scope of the queries, but we can also allow for that redundant reachability based on how routes are going to be leaked from one peer to the other. It's kind of a generic example in this case. It doesn't really give us any specifics on how we can do that. But again, that's not what the point of this particular class is. You learn about leaking routes and stub features and whatnot in the advanced routing course. And the idea is that you kind of think about how that would come into a design scenario when you're implementing an EIGRP design. Okay? So, again, we're not really seeing the specifics here, but let's say, for example, I have connected in summary, right? Now, when I say connected in summary in this case, we're not talking about what we're talking about connected routes. So this 10.1.1.0 network, right, is what we would consider a connected route. It is connected, that's true, but it's also part of EIGRP. So in order for any type of route to be advertised from one EIGRP peer to another, it has to be part of EIGRP. So it's not just simply connected routes. It's connected routes that are participating in EIGRP. Okay. So in this particular case, 10.1.1.0 is connected. Now, we've configured this router as a stub, which says don't query me. So B will never query D. C will never query D if we lose a route from the corporate side. Okay. But because 10.1.1.0 is connected, that 10.1.1.0 network is going to be advertised here, and it's going to be advertised. So C will know about the 10.1.1.0 network, and B will know about the 10.1.1.0 network. But guess what's going to happen? It's not going to go to A because it's not a connected route on C, and it's not a summary route on C. Now, you could create a manual summary. You could go into this interface and summarize the same network. So you could summarize the /24. In other words, creating a summary that matches the learned route that we got from router D. And in that case, it could be advertised. Or you could, well, I'm trying to think of a better way maybe possibly of doing that, because we have connected, we have summary, we have redistributed, we have static, which is basically redistributed static routes, and we have receive only. So that would be the only way we would be able to do that without leaking, without doing a leak feature that says, you know what, we're going to do connected and summary with the exception of the 10110 subnet. So even though the book doesn't really describe this, what they're talking about in this particular case is they're saying, you know what, we would probably leak out the 10110 subnet over to router A, essentially as an exception to the rule of what the stub router is advertising to its peer. All right. And conversely, we would probably leak out the default route from C to D and from D to C in each direction, or at least in one direction, so that we would have redundancy in that direction as well. All right. That's an option that we would be able to do. Again, not looking at the specific configuration, but that's the scenario that they're talking about here. All right. Now, outside of summarization, outside of route filtering, outside of these other things that we've kind of talked about, what other types of tools can we implement in EIGRP to achieve faster convergence? The process of convergence really relies on or by definition, I should say, is defined as how long does it take for the devices to understand or react to a change in the topology. A positive change meaning additional links might come up, or a negative change meaning links might fail, right? Now, you might consider a scenario where you have routers that are peers. Let's say, for example, I have a WAN circuit, and I've got this router here, and that router is connected to some sort of WAN cloud, right? And then there's another router on this side of the link. And we got various networks that sit behind those routers. And of course, they're sharing routing information. Right? And they're neighbors. The WAN is some sort of layer 2 WAN. We're not doing a layer 3 VPN. We're doing a layer 2 WAN. So technically, these routers become peers, and they're adjacent to each other. Now, EIGRP has built into it a mechanism for neighbor loss detection. And that mechanism is called a dead timer. We have a hello time and we have a dead time. 5-second hello timer, 15-second dead timer, depending on the type of circuit. We'll just go with the fast one. 5-second hello timer, 15-second dead timer. We can rely on that, right? If this link were to fail, convergence would be relatively slow, because we would have to wait for the dead timer to expire in order for us to identify that peer no longer exists. That's a really important concept. Now, if it was two directly connected routers, we don't have to worry about that, because if the link fails, the physical layer status of the link goes down, and the router's smart enough to know, hey, the link failed, so we obviously don't have an adjacency on that link anymore. That's not the case when you have a WAN in the middle. There's some device here that's attaching those routers, some device that's allowing those routers to communicate. This link fails, we do not lose our layer 1 status on that link, so the router has to wait for that dead timer to expire in order to identify that particular peer no longer exists. And then, convergence time is going to be really related to whatever cycle we are, whatever interval we are at with that dead timer in the overall cycle of hello and dead timers. All right. So layer 2 failure detection can take a lot of time, and even on slower speed links like NBMA networks that are below 768 kilobits. Now we're talking about a 60-second dead timer. As opposed to, actually, is it 60 seconds? I'm trying to think. It's 120 seconds, I believe. No, 90 seconds. Because I think it's 30 and 60 and 120. I can't remember. Dang it. Such a basic concept. But anyway, it's a long time, right? So we can implement an additional feature called bidirectional forwarding detection. BFD is a fast failure detection technique. It uses keep alives. Doesn't matter what the physical layer media is. It doesn't matter what the encapsulation is. It doesn't matter what the topology is. And in fact, it doesn't even really matter what the routing protocol is. BFD is independent of all of those things, but it works with multiple routing protocols. And our detection times can go from 5, 10, 15, 20, 30, 40, 50 seconds down to less than or about 50 milliseconds. So that's a pretty significant change, to be able to do this. Now, again, we're not going to get into the specifics of BFD and how BFD works, but overall, it's kind of a basic physical layer keep alive mechanism where we identify the liveliness of an endpoint based on its reaction to keep alive messages that are being sent. It is used at the protocol layer, but it's not specific to a protocol. So it can be used for EIGRP, it can be used for OSPF, it can be used for BGP, it can be used for ISIS, and so on. One BFD session gets established between the two BFD clients that are communicating. They're sending these keep alive messages, which is called the control packet, with a detection timer. Those are configurable thresholds that you can set up when you set up the BFD process. And that's going to tell the responding client or one of the clients that are participating if there's a failure in the process. And then BFD will then notify the routing protocol that it's being used with to allow the routing protocol to identify that the peer no longer exists. All right. So BFD is a protocol that runs between two systems. The control packets are sent as unicast packets to the BFD peer. That BFD implementation then encapsulates those BFD control packets using UDP, specifically UDP port number 3784. And then EIGRP allows us to identify how the neighbors are communicating, right? What is the peer address? How are the peers being addressed, and who are we monitoring in that particular session? BFD does not do neighbor discovery, doesn't do dynamic neighbor discovery, doesn't send out multicast BFD messages or anything like that. It is a transport layer protocol. So being that it runs over UDP, so it does rely on the underlying EIGRP process or OSPF process or whatever to establish which peers are going to be communicating with the BFD messages. All right. So BFD runs on each router. We create this control packet. Those packets are sent at a minimum of 1 second intervals until the session is established. After the remote router receives that BFD control packet, it copies the value of what we call a my discriminator field into its discriminator field. It sets the flag, the H flag, which is the I hear you flag, for the subsequent BFD packets that get sent. All right. So basically, we've established this kind of adjacency, if you will. It's not really, I mean, we can do like a show BFD sessions and look at the BFD establishment, right, between the two BFD peers. But the idea is that we're not relying on kind of these classic macro timers, right? We're using these micro timers to negotiate this BFD session. But BFD is much more, much less process intensive, right? The thing about hello packets, some people might say, well, can't I just adjust the hello packets to sub-second intervals and the dead timers to sub-second intervals? But those are CPU processed functions, right? Whereas BFD is kind of almost like I don't want to say it's a physical layer concept, because it really isn't. It is a network protocol that works at the transport layer, but it's much, much less intensive, right? Like I said, BFD doesn't have a discovery mechanism on its own. We have to explicitly configure BFD between the endpoints. And it does, the nice thing about the protocol is it works on lots and lots of different underlying transport mechanisms and different layers. And it operates independently of all of those. You could monitor, for example, MPLS LSPs, and you could use LSP ping packets, for example. Any kind of adjacency setup, any protocol that relies on an adjacency setup, OSPF, ISIS, BGP, could use a Bootstrap as a BFD session. And that keep alive mechanism is how it works. Now, BFD itself can operate in two different modes of operation. It can operate asynchronously, or what we call demand mode. Now, if we're operating in asynchronous mode, both the endpoints periodically send their hello packets to each other. And if a certain number of those packets are not received, that session or that session itself is considered to be down. In demand mode, no hello packets are exchanged after the session is established. It's basically assumed that the endpoints have other ways to verify connectivity to each other, maybe at the physical layer, but we could still send hello packets if necessary. Typically, we use asynchronous mode because the whole point of implementing BFD is that we cannot rely on those physical layer, meaning that the devices are physically attached to each other. All right, so typically we're going to run in asynchronous mode. Okay. Now the timers themselves are negotiated. The timers can be renegotiated at any time. And of course you can set the timers asynchronously, which means one device might have a different set of timers than the other device. One peer could be sending control packets at 50 millisecond intervals in one direction. The other one might be sending packets at 150 milliseconds in the other direction. But as long as each of the BFD peers receive those control packets within their timer, their threshold, right, what we call the detect timer period, then that session is going to remain up, and we're going to report back to the routing protocol that everything is great. And we maintain the adjacency. But if we don't get those control packets within that detect interval, we're going to tell the routing protocol that the BFD session is failed, and the response of the routing protocol is going to be basically to drop the session itself. Does that make sense? So again, we don't really talk about the specifics of the protocol, right, as far as how do we configure it and so on. But that's easily identifiable in Cisco documentation. If you go to cisco.com and search on configuring bidirectional forwarding detection for EIGRP, you can find lots of different documentation on that. You can also reference the RFC. I think it's RFC This has been around since about 2010, 2009, 2010. Don't quote me on the exact date, but I believe it's been around. Juniper, some guys from Juniper actually came up with a concept, but I think it's RFC 5880, if I'm not mistaken. There might be some subsequent RFCs as well, but it talks all about how the BFD process works, and you know, it's a little light reading for you if you're interested in learning more about BFD. We also have some videos on our website, our YouTube channel, that allows you to kind of go through the details of BFD and so on. So take a look at those. All right. So there are some other features that we can implement as well to help speed up convergence. Two of these things are Graceful Restart and what we call Non-Stop forwarding. Okay. EIGRP Graceful Restart introduces support for something called non-stop forwarding. And the basic idea is this. There is a device with two route processors, maybe even running some sort of multi-layer switching, okay? And there are other devices, which are neighbors, that can act as helpers, which are also NSF-aware devices. When routing sessions get set up, those two parts negotiate their graceful restart capabilities, all right? NSF-capable devices can be helped by NSF-aware neighbors during something called route process switchover. Basically, the NSF-capable device has to switch over the information that it contains for the neighbor adjacencies and the routing information and so on. So we're talking about routing that is occurring in a routing that's occurring kind of in a concept of where we have multiple route processors and so on. It's not a process that you typically would think about. It's not really something you have to configure. It's just something that EIGRP kind of does behind the scenes. And the whole point of the concept is to allow what we call a graceful shutdown. We can see that we have kind of our successor route processor, which is our primary route processor. We have our feasible successor route processor, which is our backup route processor. And the idea is that we're able to essentially kind of shut down one of the processes that might fail, but still maintain all of the appropriate adjacencies and everything else that we need to have in order for us to do essentially what we call non-stop forwarding, which means that we're not going to lose any packets in the process of routing and so on. So the idea is that we're going to allow for our neighbors to quickly converge when your router stops running EIGRP or EIGRP fails on a particular interface. All right. Now, again, it's not really something that you have to configure. EIGRP uses hold timers to decide when they're going to drop a neighbor, assuming we're not running BFD, which we just talked about. And as long as you keep receiving hello packets, that hold timer is going to continue to reset. And if you were to actually go to a router and do a show IP EIGRP neighbor and you refresh it and refresh it and refresh it, you would see that the hold timer continues to refresh every single time you get a hello packet. Now, what happens when we lose the adjacency? Once the dead timer expires, assuming we're not running BFD, then we lose our adjacency. And this is where graceful shutdown comes into place. We need to speed up this convergence process. Now, generally, my recommendation would be to use BFD. BFD is a standard approach to sub-second convergence. But if BFD is not available, or if you don't want to run BFD, graceful shutdown can come into play. All right. So what happens if we lose an adjacency and graceful shutdown is in place? Instead of waiting for the hold timer to expire, we receive a peer termination message. R2, router B in this case, is letting router A know that it has stopped using EIGRP on that interface, or the EIGRP process is not running anymore. Basically, the way that works, and it's a little bit confusing. In this case, they're calling it a goodbye message. It really depends on the iOS version that you're running. Peer termination is kind of more of a modern term that we use to describe this process, but goodbye message is kind of the same concept. But if you think about it, it's like, well, if EIGRP is not running, how am I delivering this particular message? Because a peer termination message basically is a hello packet specific to EIGRP with K values that are all set to 255. If you actually go and do a Wireshark capture and see that, you would see K1 is 255, K2 is 255, K3, K4, K5, K6, and so on. All right. So it is, that's the part that's, I don't know, kind of confusing a little bit, because it's like, well, how is it doing that if EIGRP is not running in the first place, right? But it's doing it, and that's how the Graceful Shutdown feature works. All right. Now, the idea, again, is to reduce the amount of time that it takes to identify an adjacency failure. All right. Or the process, the EIGRP process failing. That's the idea. That's what we're trying to do. It's all about speeding up that convergence process. In this particular example, router A is using router B as the successor for lots of routes that it's learning. Router C is the feasible successor. Now, normally router B would not tell router A if the EIGRP process on router B went down. All right. Router A would have to wait again for that hold down timer to expire for that to happen. That goodbye message that I described, which is a hello packet, again, not sure how that happens. That's kind of one thing that's always kind of confused me a little bit. If the EIGRP process is shut down, how can I send a hello packet with all those K values maximized? But that's how it works, right? Basically informing router A, hey, I'm done. I'm not doing EIGRP anymore. So don't wait for my dead timer to expire. You can go ahead and start using router C as your destination. All right. Now, with Graceful Shutdown, that goodbye message is broadcast, and that's just to allow any peers to identify that that's occurring. Graceful Restart, on the flip side, allows us to reestablish that adjacency quickly. Now, if you're using multiple route processors and so on, you can use things like in-service software upgrade options. You can do stateful switchover to be able to switch from one route processor to another without losing adjacencies and so on. Stateful switchover allows us to switch over CPU functions from one route processor to the other. And then Graceful Restart allows for the continued forwarding of those data packets. And so we're not losing packets in this process. All right. All right. Graceful Restart is available for most of our modern routing protocols, not only EIGRP, just like bidirectional forwarding detection is available. EIGRP supports it, OSPF, ISIS, BGP. They all have Graceful Restart options. Okay. All right. Next thing we'll talk about here is using summarization and ensuring that we don't create black holes with the summarization. So what you're looking at in this particular topology here is a hub and spoke topology, but it is a multi-homed hub and spoke topology, what we call dual homed. which is there to provide redundancy, not necessarily transit routing. That's a very important concept to understand as we talk about this particular concept. Those spoke routers are not supposed to be transit routers. In other words, just because we have redundant links doesn't mean we want to make use of those redundant links for routing from A to B. We want to use the back-end network that A and B have in order to route. But with this particular redundant design, there are some things to consider. If I'm summarizing with dual-homed hubs, that summarization discard route, could lead to a black hole. Now, what do they mean by a summarization discard route? Whenever you do summaries on a router, there's always going to be a route that is created, which is called a null zero route. It is a way for us to ensure that we're not routing for networks that don't exist. And so if I create a summary for A, on that same router that's generating that summary for A, we're going to have a null zero route for A as well. Meaning that we're going to create this black hole, if you will, this what they call a discard route for that summary that we're advertising to our peers. All right. Now, it's possible in this case that we could create a black hole in this case. The discard route always has a lower administrative distance than the other routes because they're actually technically considered connected routes. Even though they're not actually connected, they're being generated based on the summarization process, they have a lower administrative distance. So when we're summarizing spoke networks towards the core from the hub routers, both hub routers advertise the prefix as a summary. In this case, let's say 192.168.0.0/22. All right. When hub A loses a connection with one of the spokes, that 2.0 route is removed from the routing table, but the summary is still being advertised because we still have the other spoke that we're connected to. All right. So incoming packets that go to that 2.0 subnet are being discarded because of that summary null zero discard route that was created. All right. We don't create that null zero route, by the way. That null zero route is created automatically whenever we generate a summary. So in essence, in this case, what we've done is we've created a black hole. All right. So let's see if the diagram is kind of, the diagram isn't really describing it very well. The default route doesn't really have anything to do with it in this case. But the null zero route is what's showing up on router A in this particular case. Now we can prevent this from happening by connecting the two hub routers and making sure that we have some sort of routing ability between the hub routers themselves. But we don't want to have summarization between the hub routers because that discard route is going to be installed again with a lower administrative distance. It has an administrative distance of 5 as opposed to the routes that are being learned through EIGRP with 90. All right. Whenever I receive the same route, the exact same route with a lower administrative distance, of course, that's the route that's going to get installed. All right. You also don't want to have an EIGRP route overriding the discard route because the whole point of having the null zero route in the topology, in the routing table, is as a loop avoidance mechanism. So say you're summarizing, let me explain this a little bit more. So say you're summarizing, let me get my pen working here. You're summarizing, I don't know, 6 or 7 routes, right? And A, B, C, F, G, H. I'm not writing numbers, but you get the idea. There's some gaps in between, right? So they're not completely contiguous, but relatively contiguous. we got A through C, and then F through H, right? But D, E, which are included in the summary, don't actually exist on the router. But because we're advertising that summary, other routers might think that they can get to network D and they can get to network E. No problem. All right. Well, if I'm advertising a summary, let's just say I'm advertising a summary of A through H, and people are routing to me for network D, for example, but D doesn't exist on that router might decide to use its default route to route the packets to D, even though D didn't really exist in the first place. So in essence, what I end up doing is I end up routing for networks that I don't own. And I might actually end up creating a loop or creating some sort of crazy routing scenario where packets are getting routed and they're not supposed to be. So that's why we create that null zero route. So when a packet gets sent to the router, the null zero route matches the summary route. If I don't have a more specific match based on the fact that a more specific route exists, then the packet will match the null zero route and the packet will get discarded. And that's really the whole point. That's really the whole point of that null zero or discard route. So if you change the administrative distance of that route, then basically you're defeating the whole purpose of what the discard route's supposed to do, and you can actually make things worse. All right. Another scenario that they walk through here is suboptimal routing. Summarizations create a more generic route. Okay. So when I summarize, it's a longer prefix. Well, actually, technically a shorter prefix. Really, it's fewer bits. It's not more bits. So summary routes may end up being less preferred simply because they have a shorter prefix length than the more specific routes. And if I'm learning a more specific route and I'm learning a summary route, I'm always going to choose the route using the more specific route as opposed to the summary route. All right. So when it comes to summarization, you need to make sure that when you're summarizing that you understand what the effect of that is. If you're looking at this diagram, it can be a little bit confusing because we've got the 10110 subnet on router A, we've got the 10120 subnet on router B, and we've got the rest of the 10110 networks that both A and B can get to. So actually, the diagram is wrong because the idea is that we are going to summarize the 10100/16 from both routers. They can both get to 10110/16, no problem. This is not my diagram. This is Cisco's diagram, but we'll go ahead and fix it here because it'll make a lot more sense when we fix it. If I just did the summary, right? I just did the summary and I chose not to leak anything else out more specific than the summary, then I may end up going up to router A to get over to network 10120, when the reality is I should really be going directly to router B for the 10120 subnet. And conversely, I should be going directly to router A for the 10110 subnet. So when you create a summary, what you can choose to do is do what we call a summary leak. You can say, okay, let's go ahead and do our summary. Trying to clear off my markings here. Let's go ahead and do the summary, but let's go ahead and also leak out these more specific routes. This one should be 10120. That would make a lot more sense, not 10110. B should be leaking out, should be summarizing the /16, but it should be leaking out this /24 for that specific network, which happens to be part of the /16 subnet. And A should be leaking out the 10.1.1.0 subnet. That way we can be assured that router C is going to use the optimal path to get to the 10.1.1.0 subnet and the optimal path to get to the 10.1.2.0 subnet. Does that make sense? Definitely makes a lot more sense when you look at it from that perspective, because their diagram is just confusing. All right. So when you're configuring summarization, you can use something called a leak map argument when you're configuring the summarization. We can still summarize the 10.1.0.0/16 subnet in this case, and that's advertised down to the dual-homed spoke. If that was all I advertised, like I said, we could end up with suboptimal routing. Packets that are supposed to go to 10.1.1.0/24 should be forwarded directly through hub A, but they could end up going through hub B, which would be suboptimal. All right. So really what a leak map does is it provides us the ability to leak out more specific routes as well as advertising the summary. We'll still summarize all the core routes, but we'll leak out the more specific routes through the summary, and we use that leak map argument to do that in this particular case. So on the right side, we should be leaking out 10.1.2.0. Okay. We did already kind of talk about the concept of choke points. When you're creating choke points in your network, you need to adjust the topology, but you also have to make sure you have the appropriate contiguous address blocks. That's a really, really important concept. If we're dealing with different choke points, move the boundary between two pieces of the network that may create a choke point that didn't necessarily exist before. And that logical boundary point between the lower routers, which in this particular case doesn't provide any ability to do summarization. Why not? Because if you look at the sales network, you got 10.1.0 and 10.1.2, and then you've got logistics kind of over on the right of 10.1.1 and 10.1.3, and then marketing and engineering are kind of split. By establishing the choke points at the sales router or at the marketing router, at the logistics router, we could potentially do summarization there. Summarizing, let's see, could I summarize sales 10.1.0 to 10.1.2? That would have to be a block of 8. I could not do a block of 4 because 4 would go from 0 to 3. So it would have to be a block of 8. And unfortunately, we couldn't do that, right? Because if I did a summarization of a block of 8 here, my summary here would be 10.1.0.0, and then a block of 8 would be 248, which would be 5 bits, which would be a 21, if I'm doing my math correctly. Yeah, /21. But here, I would basically have to do the same thing, because this would include 0 through 7 in the third octet. 1 and 3 are included in that range. So basically what they're saying in this particular case is based on how this has been created, how the topology has been created, and how the routers have been addressed, it limits our ability to do summarization at these kind of logical boundary points in the topology, because we have these non-contiguous blocks of addresses that are being used. So instead, what we might do is we might change the summarization point from this point here, which is not possible in this topology, and we might shift it up to this router here. Certainly we can do summarization on this router going up because we have contiguous blocks at that point. So that's something to consider. I would say that's a good option, but again, that would have to be something that would have to be pre-planned. So that's our next diagram here. Let's go ahead and summarize. They did a /22. So they did a block of 4. That's not going to work. That's not going to work. Let me check the math on that real quick. So a /22, that is 6 bits. So that's a 128, 192, 224, 240, 248, 252. That's a block of 4 in the third octet. So that's another typo. Those should be /21s. You can't do a block of 4 because that would only include 0 through 3, which wouldn't even cover all of the sales subnets. You would have to do a /21 because you want to cover 0 through 7. So /22 is 6 bits because 16 plus 6 is 22 in the third octet. 6 bits is a 252, right? 128, 192, 224, 240, 248, that's 5 bits. And then 252 is 6 bits. 256 minus 252 is 4. That's a block of 4. So that's only going to cover 0 through 3 because we're starting at 0. Same thing with the 2.0 subnet. So we need a 248 because we want to cover 0 through 7 because we have 0, 1, 2, and 3. Ah, there we go. I don't know why I was thinking 4 was included in that. So it will work. I did all that, and then I discovered that their math is actually correct because 0 through 3 is in fact a block of 4. So actually their summary is correct. I don't know why. For some reason, I had it in my mind that there was an additional subnet in there. But yes, /22 would work because we're summarizing network 0, network 1, network 2, and network 3, which is a block of 4. Now, if we were including the 4th subnet, then we would need a block of 8. So those /22s are correct. All right, not a typo. I'll give Cisco a pass on that one. All right. Same thing would go for the 10.2.0.x subnet, right? 0, 1, 2, and 3. We can summarize those in a block of 4 as well, starting at 0 with a /22. But I mean, that wasn't the point of the exercise here. The point here was that, oops, let me turn off that marker there. The point was that we could not extend the summarization boundary down to the spokes because the summary that sales would have to generate would be the same summary that logistics would have to generate. Then you might go to that router, that upstream router, and say, okay, well, if I want to send a packet to 10.1.2, I'm going to end up load balancing because if the metrics are the same, I potentially could end up load balancing, or I might even just do routing for the 10.1.2 to logistics when the 10.1.2 exists in the sales area. And then I won't have any routing available. All right. All right. So that concludes our discussion of EIGRP. Our next section will be talking about OSPF. So we'll see you there.